Let's go ahead and start it. Okay, today we are going to go over one of the important, and they go by the method tree-based methods or ensemble schemes. How many of you read the chapter? I think it's chapter 8 or something, right? Tree-based methods in that book, ISLR. No, no, getting there. It's an easy book. I mean, there is another book, right? I mean, ESL, which is much more harder. This is like a easy read. I mean, you can just lie down and just read like a novel, right? I mean, it's not too complicated, right? But yeah, I mean, these are one of the very important schemes, ensemble schemes in machine learning. Okay, so any machine learning algorithms or it's not complete without knowing these kinds of tree-based methods. So let's go over that. Today we will be going over very important classes of uh, tree-based methods. One is decision trees. Okay, so decision trees are very critical part of ensemble schemes, which are much more easier to interpret, right? And there are so many problems with it as well as advantages. So we will be going over the limitations of it and the classes of decision trees, right? I mean, you can have variations of these decision trees, and they go by the name bagging, bootstrapping, etc., and boosting. How many of you have heard all these names? Bagging, bootstrapping, okay. And we will see why they work, right? I mean, how they work. And I think last time we saw how the bagging schemes really work, right? Or the bootstrapping works, right? We had some mathematics behind how they work, but we will be going over that again today. And we will also look at random forests, right? What are random forests and why random forest actually works, right? That's one of the critical questions that needs to be answered. And any algorithm that you know without understanding its limitations or why they work, it's just incomplete. I mean, you can't claim yourself as an expert in machine learning unless you learn its limitations and why they work and they don't work. Okay, so we will go over that, and at last we will see a specific application of these random forests by a name CASM, which uses these techniques to predict driver and passenger mutations, and we will see in general, right? Uh, so what's classification? I mean, basically these are classification algorithms. Although there is also a regression tree, you can use regression in the framework of these decision trees, right? We will be briefly going over that, but not in detail. So given a collection of records, right, you have a training set, and each record is a set of attributes, right? And then there is probably one or more attributes by the name classes or labels, and you have to find a model for the class attribute as a function of the values of other attributes. So that's the essential idea that we are doing in machine learning. You have to find a model. You have a predictor variables and a response variable, right? And so you're trying to find a model for the predictor variable in terms of the for the response variable in terms of the predictor variables, right? With the goal that previously unseen records should be assigned to the class. So if you're given a testing data, your model should be able to accurately predict, right, where the response is going to lie, right? And so they usually you divide it by training and testing sets, right, as a measure of performance estimation, right? We studied last time. We also saw the regularization methods in context with cross validation schemes, right? So these are some of the ideas that we are doing at classification. So for instance, here you have a data set, right? You have the ID here, and also the attribute 1, 2, 3, right? I mean, and you can the idea is to have this data set, right, to a model, and there is going to be a learning algorithm, and then you apply the model for the testing set to deduce what the class labels are, right? So this is a general schema of the algorithm. So for instance, predicting tumor cells from a context of biology, predicting whether cells is either tumor or not is one classic application of classification, or classifying credit card transactions, right? These are some of the standard examples of where you could use classification. And also of late you can see that there are so many applications of it, right, including decision tree, and then there are several algorithms. Okay, so in the next class we will go over support vector machines. Those are different types of algorithms that can be used for these kinds of machine learning, right? So for instance, this is a classic example of a decision tree, right? You have these attributes, you have a data set, and then you have an attribute here which says if the tax is refunded, that if the money is refunded, that's the attribute here, and the marital status of the person, whether he is single or he or she is single or married, and you also have the taxable income, and then you classify whether the person is a cheat or not, right? So this is example for a data set. So what one can do is you can make a tree, right? And then you can classify these class label in terms of whether the person is a cheat or not. For instance, you can have a refund, you can split along the refund, and if the refund is yes, he's not a cheat. If the refund is no, then you can look for marital status, and if he is married, then he's not a cheat, or he or she is not a cheat. And then you classify along this attribute, which is the taxable income. If it is lesser than 80,000, no, or if it is greater than yes, right? So this is one of the decision trees that you can make. And one classic advantage of such a decision tree is that what? What's the biggest advantage of this model? It's easily interpretable, right? You can look at the model and then you can really understand what's going on in here, right? I mean, it doesn't need too much of an explanation, right? Rather than putting it in some data set and some higher dimensional space and trying to classify it, right? So this is much more interpretable, right? So that's the biggest advantage of decision tree. For instance, in the last example, we saw that the splitting attributes was refund and marital status and taxable income. Instead, you can categorize it as from starting from marital status, and then you can go to refund, and then you can go to taxable income, right? So the same data set can be made into a decision tree in several ways, right? So there could be more than one tree that fits the same data, right? So what's the best tree here? Okay, so these are the questions that we'll try to answer, okay? So once the decision tree is built, right, the model can be used to test unclassified data. So for instance, you have this test data, and then you have the attributes as no, married, and 80K. You can go through the decision tree and then say that, oh no, then we have to see the marital status, and if he is married, and so you can assign the cheat label as no. Okay, so that's the idea behind the decision tree, that you can easily test an unclassified data and then assign the class label. Okay, so here is an example for a kind of a regression tree here in terms of the data set. You have a tumor classification. You have a bunch of samples for tumor samples for the patients. Okay, let's say that there are two genes, gene 1 and gene 2, and you have expression values. Okay, so for instance, in gene 1, the person's expression value is somewhere like say 0.5 or something, or this is like say 3 and 0.5, etc., etc. You have some data here, and you also have the samples from patients who don't have a tumor. It's a normal samples or the control samples, and you also have the expression, right? Now what you can do is you can split the data at x equals 1, okay? And you see how, and then you can see that if x is less than 1, you can further divide the data as y is less than 1 or greater than 1. And you can split it as if x is greater than 1, then you can divide the y-axis, right? And then you can finally classify what are all the things that are the leaf is labeled as a control or a tumor based on this decision tree, right? And so if you are given a test data here, the new test data is given by that, then you can see that you can go through the decision tree, right? And then classify this as a tumor, right? So that's the idea, that you can use this tree for numbers as well. It means one of the good advantage of these decision tree is that it doesn't depend whether the data is categorical or numerical. You can apply the same algorithm, same methodology to classify the data. So that's the good advantage of this kind of a model. Or you can divide. I mean, you can divide this into several other categories, or several other what is, planes or something, but then it will not give you a robust answer, and this is a better model when it comes to this type of a classification, right? So there are pros and cons for different types of algorithms. Now, decision tree algorithms, there are several algorithms. So as I was telling you before, right, there are several ways you can split the tree, right? You can decide on what attribute you have to make a tree, right? And depending on, and also there are several metrics that we will see. Depending on that, there are several algorithms for these kinds of classification and for these trees. And one is the ANS algorithm. It's one of the earliest algorithm. And there is CART, which is classification and regression trees. And there are ID3, C4.5, etc., and SLIQ Sprint. These are some of the algorithms for these decision tree. So, for instance, for the Hunt's algorithm, right? In general, this is the idea. So, what you have is, let DT be the set of training records, okay, at node T. The general procedure is this: if D is an empty set, it's by default classified as a leaf node. If D has records that belong to the same class, right, then T is a leaf node labeled as YT. So all of the elements belong to one class. You don't have to split, right? It's perfect now. So you don't have to do anything. And if you have some records, okay, that belong to more than one class, you use an attribute test to split the data into smaller subsets, okay, and you recursively apply the procedure to each subset. So essentially, you see if there are lots of class labels belonging to the same data set, you recursively divide it. It's a simple algorithm. So for instance, let's do this algorithm for this data set, right? So you have the don't cheat attribute, and then you can see on refund variable, right? And if the refund is yes, yes, and yes, all have only one class label as no, no, no. So that's a leaf node. You don't have to split anymore, okay? But if the refund is no, right? If the refund is no, you still have some cheating labels as yes. So you go ahead and divide the tree based on marital status, let's say that. And now, if the marital status is married, you just have don't cheat as the only class label. So that's a leaf node. You don't have to split it anymore. Now, if you're having the marital status as single or diverse, it's cheat, right? And so you go ahead and split the tree again based on taxable income, and then you end up with leaf nodes. So the leaf nodes are always don't cheat, cheat, and don't cheat. Okay, so that's the idea behind this Hunt's algorithm. Clear? Questions? Nope. Okay. So the idea is simple. It's a greedy strategy. Every time you split the records based on an attribute that optimizes certain condition. So you take an attribute and see the class label. If they belong to the node, all of them belong to a certain node, you don't split it. If yes, you take the next attribute. Okay, so you sequentially goes. It's a greedy strategy, right? So the main questions are how to determine the split. Do you do a binary split or a multi-way split? What do we mean by that? I'll show you an example, okay? So how do we split the records? How to determine the best split? What's the best split here? Okay, is having, when you say that all the nodes have a same class label, is it okay if it just has one record? Right? So that's a question. Determine when to stop splitting, right? That's closely related to that. So for instance, you have a multi-way split and a binary split. So for instance, if you have a car type, you can split it as a family car, sports car, or a luxury car, right? So that is a multi-way split. Whereas for a binary split, you always divide the values into two subsets, okay? So for instance, a car type could be a sports or a luxury or a family car. You can club the sports and luxury in one category, right? And then the family into other category, right? Similarly, what you can do is you can take the car type, as you can take club the family and luxury together and have the sports different, right? So this is a binary split, and this is a multi-way split, right? So for instance, when it comes to numbers, you can do the same thing. Is the taxable income greater than 80? So if yes or no, you can do a binary split. Otherwise, you can do a multi-way split saying that if the taxable income is less than 10k, or is it falls between 10k and 25k, etc., etc. Or this is a multi-way split. So what's the best way to split, right? For instance, here you have a color that you can split it based on green, yellow, or red, and also you can see the size. If the size is huge and the color is green, it's probably a watermelon, right? And you can do it based on these attributes, in which the size could appear twice and the taste could appear several times, and the same leaf notes could appear several places, right? So what's the best way to do it? Is binary split better than multi-way split, or multi-way split better than binary? What's that? Binary is splitting only with two attributes, right? You can do an yes or no question here. Or for instance, you can do like a car type, you can club sports and luxury into one and family into another, right? Instead of doing it as a multi-way split, you can have a car, family, sports, and luxury. Well, whatever. So let's say that in terms of uh, um, accuracy, or whatever that you feel is. Do you see that there is a difference between those two, or no? I should put it that way. Really? Okay. Why is that? Something else. Uh huh. All right, but actually, you have to think it a little deeper, and so the thing is this, one of the key things to notice is that any multi-way split can be written as a binary split. Okay, so for instance, here instead of asking the color as green, yellow, or red, you can ask it whether the color is green, and then have an yes or no split, because ultimately it's categorical, right? Or instead, if you have a quantitative, you can have an interval instead of categories. Okay, so the key observation is this: any multi-way split can be written as a binary split. Okay, so it doesn't matter at the end of the day if it is a binary split or a multi-way split. You can as well use work with a multi-way the binary split instead of working with a multi-way split. Okay, so for all practical purposes, you can use the multi-way split instead of binary split instead of the multi-way split, right? So for instance, in each of these, you can ask the question: is size is big? Yes or no? Yes or no? Right? I mean, you can just proceed. Yeah. Is binary quicker than multi-way? It depends on the height of the tree. But at the end of the day, if there are n um, if there are n no if there are n values, if you construct a tree out of it, it is n log n, right? That's the height of the tree. So at the end of the day, it doesn't matter. The complexity is concerned, it's going to be almost the same. I mean, it's not going to really improve on the computational time as fast or anything. I mean, it would be negligible. So so that for all practical purposes, you can work with a binary split instead of a multi-way split. Okay, yeah. Which one? Logistic regression? Uh huh. Two groups instead of several groups. Yeah, logistic regression is usually applied on two groups. No, this is actually, yeah, this is for the qualitative data, right? I mean, yeah, but it is similar to the when you have the quantitative data, yeah, this will come under the regression tree. Essentially, that's what you're doing here, right? So now the question is determining the best split, right? Before splitting, you have, let's say, the 10 records of class 0 and 10 records of class 1, right? So you can split based on owning a car, right? If you have S, you have the class 0 is 6, class 1 is 4. If you have no, it's class 0 is 4 and class 1 is 6. Or you can split it based on car type, and you will have these, let's say that these values here, or student ID. You have what attribute is the best for splitting? How do you determine which attribute is the best for splitting? So yes, so that's what you have to think deeply about it. There is something called greedy approach, right? So at the end of the day, looking into what actually we are trying to do. We are trying to club together the things that fall into one class, right? So what at the end of the day, what we would want is to just put everything so that all the all the attributes, all the labels that fall into one class are homogeneous, right? They should have one. It's best to have the homogeneity of the data, right? That's what we are trying to do. So we need a measure of nodes impurity. So if there is a node, we need to see how much of that node contains classes from a different labels from a different class, right? If that's the case, we don't want that, right? We have to minimize at every step of tree construction. We have to minimize the node's impurity, right? That's the idea that we will do, right? I mean, every step, it's a greedy approach. At every step, we want to see that all the nodes should have all the values, right? The node should have a homogeneous class. That's what we are trying to do, right? So, for instance, if you have a node here, a C0 as 5 and class 1 as 5, this is highly non-homogeneous, right? Whereas if the class 0 is 9 and class 1 is 1, it is highly homogeneous, because all this belongs to class 0, right? You can't say something like that here, right? So at every step, we need to find out what's the measure of impurity. And there are several measures for impurity. The famous measures are Gini index, and there is something called entropy, which is based on the physics concept of entropy, right? And also there is something called misclassification error. Okay, so these are given by this matrix. The Gini index is given by the 1 minus negative of this probability, right? So how do we do that? Let's say that you have, before splitting, you have that class 0 and class 1, right? You have these nodes 0, 0 and n1, right? Let's say that you are splitting in terms of attribute A, and we have these values here. So what we will do is we compute some measure of impurity, right? This is the measure of impurity for this node, and you have the measure of impurity for this node. And if you split it on the based on this attribute B, you have the measure of impurity as M3 and M4. And so we will compute something called gain. Okay, it's the gain of information, whether this is best or this is best, right? So that's the essential idea. So for a Gini index, right, that measure of impurity is given by 1 minus the summation of this value, where P of j given T is the relative frequency of class J at node T. Okay, so for instance, let's do a Gini index for this node. You have a node A, and sorry, you have an attribute A and you have a node n1 and n2. Okay, so let's say that you have class 0 as 0, the C0 is 0 and the class 1 is 6 here, whereas for this M2 you have the class 0 as 1 and class 1 as 5. Okay, you can compute the Gini index, which is probability of j given t, right? And that is, you can for this you can see that it's just going to be 0 for this node. And similarly for this node, you can see that the Gini index is going to be 0.278 for this M1 and M2, right? Now, this splitting is based on the Gini index is used in several of these algorithms, CART, SLIQ, and Sprint. And then what you do is, at any point when you are trying to find out whether what attribute to use, you compute this quantity, which is a Gini of the parent minus the Gini of the left, and then the Gini of the right, weighted by this number NL by n parent and a number of nodes in R by n parent. So number of records. So once we find this measure, we can split that maximizes the Gini split. So for instance here, right, you have an attribute B, and then for parent it's 6 and 6 here, so the Gini is 0.5, and you can compute the Gini for N1, which is 5 and 2, and then for N2 it's 1 and 4. We can compute the Gini index as 0.333. Now the Gini of children is going to be the value here, 5 plus 2, 7 by 12 times this plus 5 over 12 times this, it's 0.33, and then you can compute the Gini split for this attribute. Okay, so for each attribute you compute this Gini index, right, and then you try to see which minimizes the Gini is going to be the best attribute for splitting. Okay, so that's the idea. And the same idea is same with entropy. It's almost the same, except for this measure, right? Except for this measure, we use the entropy measure, which is logarithm, right? P log P. Okay, so the idea is essentially the same. At every node, right, for every attribute, you compute the Gini index or entropy or a misclassification error, and then you see which minimizes that, and then you see that whether that attribute is best for splitting. Okay, so for instance, the entropy, it's going to be 0 log 0 here for the parent, and you can see that you can compute the same things. I mean, it's no different than Gini index. So, but then it's also one of the I mean, there are some disadvantage and advantage in using, because these are different measures. Some algorithm may be working better on some data set, and some on the other, some may work better on the other data set. It also depends on the data set. But in general, you can use any of these measures, or you can use each of these three measures, right, and then try to come up with the best actually for your final classification with the testing set. Okay, you can use a cross validation schemes along with these three measures. That's a very that's a better way to do some of these things. So so this is used in these algorithms ID3 and C4.5. But the disadvantage is that this tends to prefer splits that will result in a large number of partition, each small but pure. Okay, so that will result in a lots of large splits. Now, the same idea is for classification error. Okay, so just like a Gini index, you use probability of I given t, the node t, right? And so you can use exactly the same idea here, except this metric is given. But there is a need for different metrics. It depends on what kind of a data set that you have. Some data set may perform poor with some of the metrics, and some may perform better, right? So for a splitting criteria, you can see that the misclassification error, right, versus the Gini index and then the entropy, you can see that they all go up, right, at 50-50, right? When you have the nodes that have a high degree of non-homogeneity, right, the errors are going to be, the misclassification errors, Gini and entropy, are going to be high. Okay, so but when it is 0, it's going to be small, right? So that's the idea here. So it's a greedy strategy. and you split the records based on an attribute that optimizes certain conditions, right? The condition is you should have a high degree of homogeneity. Now, we asked the question on how to split the records, binary or multi-way split, and we found out that it's same as the binary split. And we have three measures for splitting the features, right? Now we can ask the question when to stop splitting. When do we stop splitting? Can we go on splitting? Number? Like, what would happen if we go on splitting? You will have a high degree of homogeneity, right? Which is good. Right. Right. So that's the key point, right? It may work perfectly good on training, but it may fail on testing. But there is also but there are some methods to do that, right? So we can't be going on splitting until you have one node in here. So one of the things that we can force is that to have a certain number of elements, right? So what we can do is one can do is one can limit, say that at least it should have certain number of elements instead of splitting just having one node each. We can put a stopping criteria. Okay, so the biggest disadvantage, as I was she was telling, right? I mean, you have it may work, it may not work on the new data, right? But you can put a threshold in here saying that each leaf should have at least 5 data points, right? When you do that, then that's a better strategy, right? So but then that also depends on the threshold too, right? So one of the things that you can do is that another thing that you can do is splitting a node, right? If it does not make any significant information gain, you don't have to do that. So at every step we find the information gain, right? So at some point you will see that the information is not gained much. At that point you can stop that, right? So there are couple of approaches here. But again, the problem is that what's the metric that's used? So for instance, when we do a Gini versus misclassification, okay? So let's say that you have an attribute A and you have a node N1 and you have a node N2, and you have in N1 you have 3 in class 1 and 0 in class 2, and in N2 you have 4 in class 1 and 3 in class 2, right? You can compute the Gini index for N1 and N2. Okay, so for N1 it's going to be 0, and for N2 it's going to be 0.4, and so you can compute the Gini for the children, right? And you say that, okay, the splitting on attribute A, it's going to give me the Gini index of 0.08. Okay, whereas for misclassification you can do the same thing. You can compute the misclassification error, and then you see that it's going to be 0. So how do we resolve this, right? You have on one hand, if you use a Gini, you have a different criteria. So how do you choose a threshold, right? And also you can see that entropy versus misclassification. You have the original tree here, and it's classified into 40 and 80, and then 28, 42, etc., right? And if you use a classification error, we can see that the values is going to be 0 here based on this classification. And for the same tree here, right, the entropy is going to be 0.02, right? So now we have a problem that it depends on actually the kind of a metric that you use in splitting. Whether you use Gini or whether you use entropy or whether you use misclassification, it matters when do you stop the splitting and when you don't stop the splitting, okay? So the big disadvantage for classification tree is that it's inexpensive to construct, right? If classifying features are given, if it's known, right? And it's extremely fast actually. Constructing a tree is pretty fast, and there are very robust algorithms for doing that, right? And it's also easy to interpret for small size trees. For small size, it's pretty easy to interpret, right? And accuracy is comparable to other classification techniques, right? For many simple data sets, the accuracy is pretty good for using the classification trees. The biggest problem would be underfitting and overfitting. When you have lots of data points in a tree, in a node, you come to a problem of underfitting. And when you have just one data point, you'll have a classic problem of overfitting, right? So it costs of classification high as tree combinatorial. You have to choose features, it's going to be combinatorial, right? And sensitive to data, it will have a high variance. Even a very small change in the data point, it's going to give you a radically different tree. So those are the biggest problems in using the classification trees. So there are other methods to stop splitting. One is using validation methods, right? You can use a cross validation and validation methods, right? So you continue to split until the error on validation set is minimum. You always have the listing and you can check how it does in the validation, right? And cross validation relies on several independently chosen subsets, right? So you can choose several independently chosen subsets and you can use that. And there are several cross validation schemes that we saw, right? What's last time we saw one of the very good cross validation, leave one out classification, right? LOCV, right? Or you can use a Clayfold class validation, right? Or there are some things bootstrap methods, right? We can all use this with this tree, right? So one of the key ideas in bootstrap aggregation, it's bootstrapping. It's the each classifier, if it has a high variance, the aggregated classifier will have a smaller variance. That's the central idea. If you have several classifiers, right, and if you take the average of those, the averaged classifier will have a small variance, right? And this is the idea behind the bootstrapping algorithm, right? One of the why we use a bootstrap is that, for instance, here you have a data point here, and you have a tree, and if data point just moves in little bit over here, it will be classified as 2, but it's highly variance. I mean, the variance would be higher for trees. For even a small data set, if it changes, the tree structure could radically change, right? So the variance is reduced by aggregating and averaging. Okay, so you remember last time we saw the bootstrapping. You remember why bootstrapping works? Why is that? Okay, I'm going to bore you with this mathematics since you don't tell me that. So you have the variance, right? You have the variance and the properties of variance. These just depends on these two properties of variance. One is the variance of a random variable is the expectation of z squared minus expectation of z the whole square, right? And also the another variation is the multiplicative, the scalar multiplication, right? Variance of az is a squared variance of z, right? So let's say that you have different data sets here, x1, x11, x21, etc., etc. This is one data set, and this is another data set. And let's say that at same point x, right, the variance is given by, for this random variable, if you take the average of the responses here, 1 over m summation of yi, right, you see that the variance of this random variable is 1 by m squared variance of summation of yi. Okay. Now there is a key assumption that if these yi's are uncorrelated, right, you can write the entire math here into two properties. The expected value of z is the same as y, and the variance of z is 1 over m variance of y. Okay. So if yi's are uncorrelated, right, you can write the variance of this random variable z as 1 over m variance of y. Okay, so what this means, as m increases, the variance is reduced, right? As m increases, the variance would be close to 0, right? I mean, you can increase as much, but we don't have several of those samples, right? So what we do, we make a uniform sampling of the same data set with replacement and use the sample set, right? So that's the key idea here. Okay, so you take some random sample of the original data set and then you construct a classifier on each of those and then take the aggregated prediction, okay, and take the consensus. So for instance, you have the training set here and then the testing set here, right? And you have the classifier 1, classifier 2 and classifier 3, etc., etc. You can take some sample, some subset of this training data set, right? Uniformly sample them. The key observation is uniform subsampling, okay, and replacement, okay. So once you do that, you can have a prediction 1 based on this classifier, and you can have a prediction 2 based on this classifier, etc., etc. And then you can use a consensus or an aggregated prediction, okay. Any questions? This is a very important concept, bootstrapping. No questions? Okay, I'll go to the next one. So if you look at the error when we take the bootstrapped trees as well as the original one, you will see that the bagged trees. Though if the original tree error is about zero point 0.5, you see that there is a much reduction in the bagged trees or the bootstrapped trees, right? So that's why bootstrapping works. Now, one of the another classic way of doing bagging is another thing called boosting, which is similar to bagging, but like what I was telling you, right? What is a fundamental reasoning behind bootstrapping? Uniform subsampling and replacement, right? So for what we can do is, instead of doing a uniform subsampling, you construct the tree, okay, and if you have lots of errors, you wait and take the class that produces more errors. You don't uniformly subsample, but you sample with the distribution. If you do that, that is what is known as boosting. So for instance, you have these training and testing data, right? You take some sub at first you saw a random subsample and you do this, okay, and then you test it with the data set, okay, and you see the error. If you have more error, you wait and take the population that has more error, okay, and then do the classifier on that population or with that distribution, okay, and similarly you perform several of those and then do the prediction, okay. Then you get what is known as a boosting, okay. There is a critical difference. It's a sequential, uh, sequentially you replace, okay. In bootstrapping, what you do is you take a uniform subsample, you replace, you take a uniform subsample, you replace, and do that, okay. But for boosting, you take the first uniform subsampling and test it, okay, and then wait the next time. Like if you take there's an urn of 5 red balls and 5 blue balls, and you take uniform subsampling of 3 and 3, right, and then you test it, and if your prediction is wrong, next time you don't take 3 and 3. If your prediction is wrong with the blue ball, you take 4 of the blue balls and 2 of the red balls, and then you do the classification again, okay. So the third time you do a different distribution of these. You don't do a uniform subsampling. You wait accordingly and then do the sampling, okay. So that would give you what is known as a boosting, and that gives you a better errors. Yes. Mm-hmm. Yes, it could be different. Yeah. So, but finally, you end up with taking the consensus anyway. So so you take the prediction, you take so what you do is you are trying to iteratively trying to do the you better and better your sampling method, right? I mean, so that you. Yeah. You take anyway. You are going to do with the testing data, right? Yeah, right. It's every time what you do is the sampling is going to be different, right? Right. But you take the fine. Uh huh. Oh, with well, that's a very good question. Whether the final model is, but then first you're using a uniform subsampling, right? So it doesn't matter. It's going to be. I mean, these things are usually done with several of the first ones. I mean, you don't really take. Okay, you take the first iteration on one subsampling, right? If you have a large sample, right? it doesn't matter. You are going to take the first one is going to be random. The second one will be, the distribution will be different. So it will not be dependent on the first one because it's only a random sampling. The first sample is going to be a random sample anyway, with a equally likely outcome, right? So it's not in general dependent on the first one because the first one is random. Yeah, first is random, but if you choose first with the distribution, yeah, it will be sensitive to the distribution. But the first in is a random sampling. So there is no such thing as a biasing in any way. You are starting with an unbiased, a random sample there, right? And then you are trying to iteratively build. So it is I mean, no way that it could depend on the first set of samples because anyway it's random. But if you take the first with the distribution, then obviously it's going to affect the distribution is going to get propagated, right? So these are the differences between backed decisions and boosted decisions, right? So you have the two features here, and you see that the boosted gives you much more better partitioning to the data, right? So that's the idea behind the boosting and bagging. So bagging can be seen as a method to reduce the variance, right? But random forest is much more. It's a modification of the bootstrapping. Okay, so in bootstrapping, what you are trying to do is you are essentially trying to take the random sample, right? Different samples of the data, and then you are trying to build the trees. But you can also think of taking different features and constructing the tree. Okay, that's the idea behind random forest. Okay, so let's say that you have rows and columns as your data. You can take the random sample of your rows, right? You can take row number 1, 5, 8, 3, 7 on first pass, right? So that is going to be bagging, but instead you can take a random features on columns. That is going to be random forest, okay? And then there is a reason why random forest works. So for instance, in tree 1, you have this division, let's say that old, young, diseased, tall and short, and you're trying to classify someone as healthy or diseased. The tree would be like this. And then another tree could be based on old, young, and male and female. This is another gender. Let's say that there is an attribute gender, and there is an attribute of work status, either it's retired or working, right? So the key attributes are the height, gender, and work status, right? And then you are trying to predict if somebody is healthy or diseased, right? So for instance, if you take this tree, in this tree the gender is absent. Okay, in this tree, whether somebody is the work status is absent, and here the gender is absent, right? So this would make a different prediction, this would make a different prediction, and this would make a different prediction, and you can take a consensus prediction out of it. Okay, so that's the idea behind random forest. Questions? Got it? You take some random features and then do a tree on it instead of taking all features. Okay, so the idea is this: you draw still you can do with bootstrapping. You can still draw bootstrapped samples. You can take some data points and then construct these trees with different attributes and then take the consensus. That's the idea behind it, right? Are you convinced? No? Yes? No? Should see the math. Okay, why it works. This simply because actually the variance of the tree, right, the variance of these 1 over b, this quantity, right, it can be written as in terms of covariance, and actually it can be split into two components, and one component is the correlation component, and the other component depends on the number of trees that you are constructing. Okay, so if you have the decorrelated trees, that will give you a better accuracy. So this variance, right, you are reducing the variance here, the variance of the prediction, right, and that would decrease if the number of trees is increased, and the decorrelation, actually based on the decorrelation of the trees. Okay, that is why you are taking as many different trees, or not as many different trees. You are taking different types of features, and then you are trying to do the classification on it, right? So we can compare bagging, boosting, and random forest. So for instance, bagging, uh, kind of, if you look at bagging, and the boosting is the lowest error, and the random forest falls in between. So in general, in terms of the error reduction, it also depends on the data set and everything. Okay, but at least the random forest is actually it's kind of falls in between bagging and boosting. Now, I was telling you last time, right? What's the biggest question in machine learning? That if somebody gives you a great algorithm and says this is one of my greatest algorithm, what's your question? What's that? Feature labeling. Uh, no, that's a testing, right? Based on the model. But what's that?
Is it validated?
What does it mean by validated?
That yeah.
So what does machine learning algorithm depend on?
Yes.
Come on, guys. It's variance bias trade-off. Okay, that's the biggest, right? I was remember that the bias and variance. There is always a difference between bias and variance. So your exercise would be to find the bias variance trade-off of these three methods. Okay, so you can take it as an exercise, but that's one of the if somebody gives you a machine learning algorithm, the first question you should ask is what's the variance bias trade-off. Okay, because that fundamentally determines, there's always a trade-off. You can't get the best machine learning algorithm. There is always going to be a problem, okay, between these two quantities. Okay, so let's go into the further applications of this. Anybody know what somatic mutations are in cancer? Right? So you have the DNA, right? ACTGs, right? You can take the DNA from the tumor tissue, and you can take the DNA from the control tissue, and then compare them, and then see where the mutations are, right? So that's the basic idea behind cancer somatic mutations. And here is a set of the scores for validated mutations, and you see that there are about 1200 mutations, out of which if the score of how quality the mutations are, it's near 15, and if the score is really higher, it has a very good chance of being a somatic mutation. Okay, so that's one of the key questions, is to determine what are all the driver mutations. You see that there are lots of mutations that happen. If you do cancer genomics and try to identify mutations, you're going to see bunch of mutations. You have to identify what's the driver ones and what are known as passenger mutations. Okay, so the passenger mutations are just like sitting, and they just travel without causing any big major problems. The driver mutations are the one that drives the tumors, like BRAF, KRAS, and all these are all driver mutations, right? So how to determine these key driver mutations? And we can look into evolution for answers. Okay, so that's the famous quote by Dobansky, that nothing in biology makes sense except in the light of evolution. That's one of the classic quotes. Okay, so what these two, the idea behind drivers and passengers are fundamentally basically evolution, right? Some mutations are being selected for tumor growth, and some would not mean, right? Selection, what does it mean? Evolution, right? So to understand selection, I think you have to understand what is non-selection, right? I mean, essentially, some mutations can get fixated in the population without even uh, without even uh, without even going through the process of being selected, right? Through the tumor microenvironment, it may not provide any beneficial advantage for the mutation, but it still get fixated in the population. It's called genetic drift. Okay, it does not mean certainty, right? I mean, genetic drift is something, the change of allele frequencies, but it can get fixated in a population. Okay, so driver mutations are not an outcome of genetic drift, but due to selection, right? So you can have a non-random process by which certain phenotypes get selected. And for example, P53 and KRAS, right? These are classically being selected, right? And if you look at the mutational frequency, there are some mutations that are being highly selected, and there's a big tail, right? Those are them, but still there could be some key mutations in there, right? So the idea is to actually identify what are driver mutations and what are passenger mutations based on random forest classifier. Okay, this is a paper, CASM. It's an old model, and I don't know whether they are still working on it. But the idea is to actually use this. So what they do is they use lots of features, like 56 features. One is the PTM enzyme. You have the SNP density, DNA binding density, etc., exon conservation, all these kinds of features. And then what they try to do is they try to have a known driver mutations. There is already a known driver mutations, and you can simulate the mutations, and then you can use a random forest classifier, and then to choose, if you are given a set of mutations, we can use the classifier to determine whether there is a driver mutation or a passenger mutation. Okay, so that's the idea behind the CASM. So it's basically you have a table, and that table takes into consideration all these things, and then it takes some statistics, and then says that, oh, this is a driver gene and this is a passenger gene. That's based on the um, uh, so this is a pipeline that I developed using CASM. But anyway, so in summary, right, decision trees, key thing that you have to note in a decision tree is that what metric that you're using, because it's highly sensitive to the metric, right? And where do you split the nodes and the limitations, right? And some of these things can be overcome by bagging and bootstrapping and boosting. And also you can use the random forest classifier. Okay, so a good exercise for you would be to work out the bias variance trade-off for these uh, three classifiers, both boosting, bootstrapping, boosting, bagging, and then the random forest. Okay, so that would really give you a good perspective on it. I mean, at the end of the day, you have to work it out. There are two modes of learning to do machine learning. One is that you take the data set, get your hands dirty. Actually, I was about to show you the lab tutorial today, but we are not going to have the tutorial today. Instead, we will have it in the next class. So one of the things is to actually work on some of the data sets and gain some experience on it. At the same time, also know some mathematics and statistics behind why some things work and why it doesn't work. That would distinguish people from, who can claim they are a machine learning scientist and the one who really, knows stuff. Okay. So I want you to go ahead and practice some of these things and get a good perspective on this. All right. All right, so I think I will stop with this for today, and you're welcome to stop by my office, ask any questions at any time. Okay, I'm in 737, so feel free to stop